In this video, we're going to talk about simulations and experimental probability. A simulation is a way of collecting probability data using actual objects such as coins, spinners, and cards. What this means is you might flip a coin 50 times to see if you truly get tails half of the time. Experimental probability is the results of conducting an experiment with probability. Many times, you'll do a simulation to see if your experimental probability matches the theoretical probability. Let's go through the following problem together. It says that the bar graph shows the results from spinning a spinner 200 times. Compare the theoretical and the experimental probabilities of the following. Spinning a 4. Theoretical probability is what we would expect to get. If we look at the spinner, there are 5 sections on the spinner labeled 1 through 5. There's 1 4 out of the 5 sections. So in theory, we would expect to get a 4 1 out of 5 times. When we compare theoretical probability to experimental probability, it helps to turn into decimals and then into percents. You can make 1/5 a decimal by taking 1 divided by 5. That's 0.2. And then 0.2 is 20%. So we should expect to get a 4 20% of the time. Now let's look at the experimental probability, which are the results we got when we spun the spinner 200 times. When we spun the spinner 200 times, we got a 4 37 times. So our experimental probability was 37 out of 200. Again, when we compare, we're going to want to make that a decimal and then a percent. When you take 37 divided by 200, we get 0.185. As a percent, that's 18.5%. So now let's compare what we got in our experimental probability to what our theoretical probability is. We were only 1.5% off. So our experimental probability was pretty close to the theoretical probability. Let's go through another one together. It says that a fair 6-sided dice is rolled 50 times. The results are recorded in the frequency table below. It says to compare the theoretical probabilities to the experimental probabilities. The first one says rolling a factor of 6. Let's find the theoretical probability first. A factor of 6 is a number you can divide out of 6. That would be 1, 2, 3, and 6. There are 4 factors of 6. So our theoretical probability would be 4 out of the 6. To turn that into a decimal, we would have 0.667. And that as a percent would be 66.7%. Now let's look at what we got experimentally. We had 6 1s, 8 2s, 10 3s, and 8 6s. We need to add up how many times we rolled a factor of 6. When you add those numbers up, we get 32, and we rolled it 50 times. To turn that into a decimal, take 32 divided by 50. That's 0.64. So we got it about 64% of the time. In theory, we should have gotten it 66.7% of the time. Our experimental probability was not far off from our theoretical probability. I'll pause the video and try the next one on your own. It says rolling a composite number. Now let's see how you did. A composite number is opposite of a prime number. A prime number has exactly 2 factors, 1 and itself. A composite number has more than 2 factors. So the numbers that have more than 2 factors are 4 and 6. In theory, we would expect to get a composite number 2 out of 6 times. That would be 0.333, or around 33.3%. In our simulation, we had a 4 8 times, and we had a 6 8 times. So we rolled a composite number 16 out of the 50 times. 16 divided by 50 is 0.32, which is 32%. So in our experiment, we rolled a composite number 32% of the time. And in theory, we should have gotten it 33.3% of the time. Our experimental probability was pretty close to our theoretical probability.